Thank you. So I will start with a quick reminder about side channel attacks. Very shortly, it's just a...
Leave it on, we'll mute it.
Okay. So it's just a scenario where the adversary can not only, I will give the example with block cipher. So we assume a scenario where the adversary not only uses the plain text and the ciphertext, but also some kind of physical leakage. And if I take this example here, it could use the power consumption of a cheap computing DAES. And I would say the main result of all these attacks is that if we don't pay attention, like if you implement a provably secure crypto system or algorithm in an unsecure device, most likely it will get broken. And that's especially the case if you consider low-cost embedded devices, because this is where we have the biggest implementation constraints. So of course, resulting of this, there's been a lot of work trying to improve the physical security of embedded devices. And I would say you have two main approaches. If I summarize, one option is to work at the implementation level, which makes sense somehow because this is where the problem lies. So it's mainly the idea to try to reduce the amount of information leakage that we have in a chip. And you have tons of papers published about this. IDs generally try to randomize either the time or the data, or try to add noise to implementation. So essentially try to make the implementation look less deterministic to the adversaries. So that's one way, and I would say a bit later, and starting maybe with the work of Michael in 2004, people have tried to deal with the problem at the mathematical level. And essentially the idea would be try to include leakage in mathematical proofs and have something that's including everything in security proofs again, and same thing. You have many different works, many different models, and so on. And if I summarize the limitations, somehow I think what I would say is that you have a big wall in between these two type of approaches. And mainly we have, we could say the implementation level approaches are successful in the sense that we are now able to build practically secure chips. But somehow this still relies on a bit of security by obscurity, and it's not always completely clear why we reach these security levels. And if I take the upper approach, so the mathematical things and leakage-resilient cryptography, the problem is more that most of the time these models are a bit disconnected from reality. So it's pretty rare that these results are actually helping hardware engineers to build practically secure chips. I will just give the example of leakage-resilient PRGs, so pseudo-random number generators. This will be the case study in the paper and in the talk, mainly because I think this is a practically relevant object. Like in practice, this is something that we need to have in smart cards. And if we take a look at the literature about these PRGs, one problem typically is that frequently you will see design tweaks. That seems more motivated by the fact that you have a model that doesn't completely reflect reality, or because you try to have a proof, but not really motivated by physical intuition, I would say. And a typical example is this stream cipher from Fox 2008, where in order to have security against polynomial time leakage functions, the authors had to double the key size and use this alternating structure. And it's really not clear in practice why we would need this type of alternating structure. So that's one type of issue. The other one is that frequently we have complex mathematical tools leading to loose bounds, and of course this is not really nice if you want to use the bounds to really quantify things in reality. And I would say the most important problem is the problem of assumptions. So very frequently these papers are using either hard to verify assumptions or sometimes completely impossible to verify assumptions. And I will just give two examples that are frequently used. You have the assumption that the leakage function could have a bounded range. This is clearly not the case as soon as you sample the physical information with a high sampling rate device like an oscilloscope. And well, we have the same kind of problems with Hill pseudo-entropy. I will come back on this later. Now, of course, if you have this, you could say, okay, we have many room for improvements. One way to do it would be to move from theory to practice, so try to have more realistic models, more efficient constructions and better bounds. And similarly, we could also try to move from practice to theory somehow and try to have more rigorous analysis for the countermeasures that we have. Try to propose sound assumptions and try, obviously, to instantiate constructions and see what it gives in reality. And somehow the idea is, in this work, try to do a little bit of both and move forward. We don't completely break the wall, but at least making some steps. So the goal really is, as usual, we would like to have cryptographic hardware that remains secure even if you have leakage. And for this, as usual as well, we will need computational assumptions, like the block cipher is a PRF. And we also need physical assumptions, like not all the secrets have to be leaked. And the main thing, or what we try to achieve, is first, for the assumptions, we would like the assumptions to be like challenged empirically. So essentially, I would like to be able to explain hardware engineers how the assumption works, what's the game, and how they could try to beat the game so that we can quantify in the end how good or how bad is the assumption and put this in the bounds. And as I said before, I would also like to have something leading to efficient constructions and if possible, with tight reductions. So that will be the outline for the remaining of the talk. I will start with the assumption that the new assumption that we propose, and it's simulatable leakage. And I will start with a few words of motivation. So if you look at previous work in leakage-resilient cryptography, I think one really important problem is always trying to model this leakage function. And summarized, I would say the problem really is that you can see this leakage function as either something very simple or something very complex. It can be seen as a complex function because somehow it solves Maxwell's equation. So it's solving a huge system of differential equations representing a complex circuit. And if you try to do that, with a computer-aided design, like even for something like the AES, it can take hours or even days of computation to get an approximate solution of these Maxwell's equations. And on the other hand, if you have the real circuit, it suddenly looks very simple because the actual piece of silicon will give you an instantaneous solution to this leakage function. So it's really difficult to model this, and if you, again, look at the literature, you will see attempts like assuming that it is polynomial time, or sometimes more, sometimes less, and it's really unclear what it actually is. So the idea somehow that we wanted to put forward, if it's so difficult to model the leakage function, maybe one solution will be just not model it at all. And that's more or less what we try to do here. So the setting will now be, we have an adversary as usual, and we give this adversary input-output access to the device and to the setup. So the adversary can send plain text to the chip. He will receive ciphertext, and also through the measurement apparatus, he will receive a leakage function that depends both on the key and the plain text. And what will be the assumption in this setting is just that this leakage function can be simulated under first the fact that we assume that the simulator can use exactly the same hardware as the target device. So somehow it ends up to say that we have Kerckhoffs's law for the hardware as well. There's no secret in the implementation. The only secret is the key. And of course, the challenging part of the assumption is that we assume it's possible to simulate the leakage without knowing the key. So without knowing all the secrets or all the state that is hidden in the device. So more formally, we say that an implementation, which is nothing else than a device and a measurement apparatus, has simulatable leakage if we can build a simulator S using the true leakage function L, such that the bit B in the following game is hard to guess. And well, summarize this game is really, you're essentially making encryption queries, and depending on the bit B, you will have two situations. Either, that's the situation on the left, you have consistent pairs of plain text key, ciphertext, and in this case, you receive the true leakage function. Otherwise, you have something inconsistent. You have a plain text, a ciphertext, but the ciphertext has not been encrypted with the correct key. And well, in this case, you try to simulate based on this, and you hope that it is hard to distinguish between these two situations. And we will not be long on this, but we have one additional generation query which just assumes the leakage of the previous round, because we frequently have this in the constructions that we investigate. And on the top of this, just by definition, we will say this simulator, that's the simple case. If you give the simulator a key, a plain text, and a ciphertext, and everything is consistent, then of course you can just use the true leakage function because you have the hardware. So that's the simple case. Again, the difficult case is when the things are not consistent. I will come back on this. But this is easy because it makes all the results depend only on the number of calls to the simulator, and you don't have to distinguish between simulator and leakage function. Okay. So I guess that's for the definition of simulatability. Now the question is, Maybe one last thing, of course, one important parameter in this game is the number of queries and queue. So the larger the queue, the more difficult the assumption is to fill. So now what I would like to do is essentially try to convince you that this assumption could make sense. And the way we do that in the paper is we propose an instance of simulator, which is not completely general. It's an instance of simulator that only works for block ciphers. But since block ciphers are quite useful in leakage-resilient symmetric cryptography, we think it's an interesting first step. So what we do for building this block cipher-based leakage simulator, we just define the leakage function that, again, depends on the key and the plaintext as the concatenation of two parts. You have LP, which is the left part, concatenated with LC, and essentially LP will correspond to all the leakage samples for the first cipher rounds, and LC, for C is the ciphertext, corresponds to the last rounds of the cipher. So more practically, this is how a leakage function would typically look like in practice. At the output of the scope, you would have time samples at the x-axis, you would have the leakage at the y-axis. All the things that you see are more or less the clock cycles of the implementation. And somehow what we assume is we say LP would be all the samples on the left of the middle point, and LC will be all the samples on the right. And that's pretty much it in terms of definition. And based on this, we will say we can instantiate the simulator just by concatenating LP and LC. And once more, if you have plaintext, ciphertext, and key that are consistent, then this is very easy. But sometimes we will need to simulate also with LP that corresponds with one plaintext and LC given on a ciphertext that is not consistent with the left key. And this is the case where it will be more difficult. So why does this work? The main reason, or the way I would like to give intuition, is coming back to how DPA works in practice. And I would like to argue that this assumption of simulatability is somehow in between really standard DPA, as we perform in general, and Hill pseudo-entropy that's much more difficult to guarantee. So if I take the example of DPA, we have the trace again, and all these attacks, they usually work by divide and conquer. So you predict something in the implementation, which means you need to be able to enumerate, and you compare this prediction with actual measurements. And if the comparison is good, then you assume this is the correct key, the correct byte of the key. And because of this prediction step, of course, you cannot exploit all the leakage samples in the trace. That's represented here. I give the example where typically you will exploit all the operations before the diffusion is complete, for example, because you can enumerate. So here it's, for example, 1 byte after the S box. Maybe you can do a bit more, but not much more in general. So that's what we try to do. Like when we try to have security against DPA, we try to avoid or to prevent all these attacks that are exploiting these samples at the beginning of the block cipher. The problem with Hill pseudo-entropy is that if you want to ensure this, you have to guarantee security against an adversary who has to distinguish between two situations. You have the real key, and then you have another key with high mean entropy, and both should be indistinguishable given the leakage. But this means that the adversary has the key in hand, and it means that he can exploit all the leakage samples in the trace, because everything is predictable in his game. So in terms of amount of information that is available to the adversary, asking to guarantee high Hill pseudo-entropy essentially means you are asking much more to hardware engineers than much less. And as usual, the goal of leakage-resilient cryptography is to help hardware engineers. We can hardly say this is truly helping. And the point with simulatable leakage, somehow the intuition is that it's just in between. I would say it's like DPA, but you can exploit the input and output leakage. So as in DPA, you don't know the key, so you cannot exploit all the middle samples. But you have the problem that the plaintext and the ciphertext, maybe it can be used in order to distinguish whether it's true or simulated leakages. So that's the point. But this is not too bad because it means that really attacks against Q simulatability exploit the same information leakage as DPA if the traces are consistent with the inputs and outputs. But if you remember the instance of simulator, that's exactly what the simulator does. It is at least consistent with the plaintext and the ciphertext, maybe not with the key. So that shouldn't be too much of a problem. There's something more, of course, which is we need concatenation. We need to be able to concatenate traces without being detectable. This is detailed in the paper, and this is admittedly something new in terms of assumptions, but I guess it boils down to the fact that we have leakage samples in these traces that contain no information or no relevant information. In synchronous devices, like CMOS devices, most of the time what we have is things are divided in clock cycles. We have a lot of activity with a peak at the beginning of the clock cycle, so a lot of computation and usually information there. And at some point, you need things to be stable to guarantee that you have the correct result in the end. And usually these points, at least in practice, that's what we find out, they contain no useful information. As I said, at least it should be easier to guarantee than high-yield pseudo-entropy, so that's at least one step. And the important point, I would say, is regarding what I said in the beginning of the talk. We would like to have things that hardware engineers can test. And we directly have nice challenges here. Like, for example, constructively, we could say, here we propose one instance of simulator, but of course you can try to design another simulator. Or another constructive challenge would be, given the simulator that we have in the paper, try to design an implementation such that the combination simulator and implementation gives you simulatable leakages. And obviously, if you want to be destructive and show that the assumption is not good in certain contexts, this is certainly true too. You can take the simulator, one particular implementation, and try to break the Q simulatability game. That's all feasible. So before moving to the end, I will just say one word about which parameters we are aiming for, because if you think about the assumption, you could say, of course, maybe just make things trivial. Why, if we can assume simulatability, why don't we just assume simulatability for the whole trace? And then the whole leakage is not useful, so for very large Q values. And the reason for this is that, again, in practice, if you look at DPA complexity, the time complexity of a side-channel attack usually decreases exponentially with the number of measurements that you perform. So this is an example coming from the DPA contest. On the x-axis, you have the number of measurements. On the y-axis, you have the time complexity to recover the key. And the color, like the grayscale, is the success rate, or the probability of success of the adversary. And what we see more or less that at the beginning it's kind of linear, and you have a log scale in the time complexity, so you really see the exponential security decrease. And in this particular example, we see that it's an implementation of the AES, and after a couple of hundreds of measurements, you're able to completely recover the key with low time complexity. So this is not good, and this is why we need to rely, as all the papers in leakage-resilient cryptography, we need to rely on some kind of rekeying. And that's the stream cipher case study. So again, what we want to do is take the most natural construction. It's a stream cipher based, or it's a PRG based on a length doubling PRG. You just iterate this one and produce an intermediate key and a new output. The length doubling PRG can be instantiated with a block cipher. So this is where we can use the simulatability assumption. And the goal will be try to remain secure after, let's say, 10 to the 6 runs of this PRG. But we just want to rely on Q simulatability for Q equals to 2 because we only use a length doubling PRG. The fact is that, like, looking at the literature proving this was surprisingly difficult, we show at Fox that it's anyway unsecure if you consider polynomial time leakages. At CCS, we show that it's fine if we consider the block cipher as a random oracle that the adversary cannot target or cannot query, but this is not completely standard. Last year at Chess, Faust showed that it's okay, Faust and other people, if it's okay if you use fresh randomness in each round, which is not very efficient. And finally at CTRC, we showed that it's also fine if you use deterministic randomness, and this is only true in Minicrypt. So nothing very standard, and what we have here is just the result without any particular assumption, simulatability, and the fact that the block cipher is a PRF. So I'll just give in 1 minute the idea of the proof. There's one lemma where we can replace, the lemma represents one iteration of the PRG. So we have one original view with the key, the next output, and next key. We use simulatability to replace the leakage by simulated ones. That's the first thing, so you can use this random key as in the Q simulatability game. And then we use the fact that the block cipher is a PRF to replace the outputs by true randomness. And well, this is only for one round. We can obviously extend this to multiple rounds with a hybrid argument. So again, we have an original view. This is an example with 4 rounds. First thing that we do is we call the simulator four times so that we replace the view by a completely simulated one. And then we make another for-call to the simulator so that we replace this completely simulated view by the original view, and only the last round is random. And as in all the previous works on similar constructions, we need to exclude the last round leakage, because otherwise you have trivial attacks. So the results really looks like what we would like to have. This last round output is uniform or close to uniform given all the previous outputs and all their leakage, if the block cipher is a PRF and if we have two simulatability. And what is nice, as I said, is we wanted to have a good security degradation, and it's just here proportional to twice the size of the number of queries. We'll just conclude. I think the main message is somehow that we can have more realistic assumptions, and in this case, falsifiable assumptions may sometimes lead to easier proofs, more efficient constructions, and tighter security bounds. And this, of course, leads to several open questions. I would say we can obviously try to challenge the assumption, try to use it to prove other block cipher-based constructions, try to check whether we can build simulators for other constructions. And, well, as I said in the beginning, this is just one proposal. It would be even better to take simpler assumptions like unpredictability or hard to invert leakages. And that's it. Thank you.